Hello and welcome. In this video, we are going to see what a derived function block, or DFB, is and when it is recommended to use one. We will also see what is a derived data type and its use cases. Finally, we will do a practical example where we will design a DFB to control a motor along with the corresponding DDTs to facilitate control management. As I mentioned before, the acronym DFB stands for Derived Function Block. If you come from the Siemens world, this is exactly the same as an FB, a function block. But if you are new to this, imagine it like this. A DFB is like a custom Lego piece that you create yourself. You design the piece once. You decide its shape, its color, and how it fits. Once manufactured, you can take 1,000 identical pieces out of the box and use them wherever you want without having to redesign them every time. The goal of a DFB is to turn repetitive control logic, such as a motor starter, analog signal scaling, or a PID control, into a generic tool. In short, a DFB is a code template or mold with memory, intended to be reused throughout our program. Before moving on, it is key to introduce a concept that we will use throughout the video: instantiation. Once we have created the logic for our DFB, it behaves like a template. Every time we use that DFB in our program, what we are doing is creating an instance of the block. This means that even though the logic is the same for all of them, each instance has its own state, its own variables, and its own memory, operating independently from the rest. In a DFB, we can define different types of variables, and each one has a very specific behavior and use. Let's start with inputs. Input variables are data that the block receives from the outside to work with. Inside the code, they are read-only, meaning the DFB cannot modify them. They are typically used for signals like sensors, push buttons, or safety conditions, and their behavior in memory depends on what we have connected outside the block. Inputs appear on the left side of our DFB instance. Next, we have outputs. These variables represent the results that the block sends to the outside. The DFB writes directly to them, and they are updated in every scan cycle. They are commonly used to send commands to contactors, activate pilot lights, or output calculated values. Outputs appear on the right side of our DFB instance. The next type is input-output variables. In this case, we are working with a direct reference to an external variable. The block reads its value, processes it, and can modify it within the same cycle. This type of variable is widely used for handshakes, for example, to reset commands, or to pass large arrays or structures without duplicating memory. This type of variable appears on both the left and right sides of our DFB instance. The input and output parts are joined by a line, allowing us to quickly distinguish the type. Then we have public variables. These are internal variables of the DFB that retain their value between cycles. They do not appear as an input or output pin on the block, but they can be accessed from the outside, for example, from a SCADA or from animation tables. They are normally used for adjustment parameters or configurations that do not need to be constantly wired. This type of variable has no visual representation when we instantiate the block. And finally, private variables. These variables are completely internal, and only the DFB's own code can access them. No one from the outside can read or write to them. They are also retentive and are used for the block's internal logic, such as state machines or edge detection. This type of variable also has no representation when the block is instantiated. Sections are the code that goes inside the DFB. This logic is blind. For example, in our case, it doesn't know if it is controlling the silo motor or the water treatment motor. When creating these sections, we can choose the programming language to be used, such as ladder, structured text, function block diagram, etc. When to use them. For repetitive elements, if you have 50 identical valves in your plant, don't write the code 50 times. Create a single DFB called valve and call it 50 times. You save time and clean up your code. This also brings an advantage. Imagine that months after finishing the project, the client asks for a change in how all the motors work. If you used a DFB, you only have to open the original block, change the logic once, and all the motors in your plant will be automatically updated. Easy, fast, and error-free maintenance. To encapsulate complex logic, if you have a difficult mathematical calculation or a complex communication protocol, put it inside a DFB. That way, in your main program, you will only see a clean block, hiding the internal mess and complexity. To create your own standard, the best programmers have their own library of tried and tested DFBs. When you start a new project, you simply import your library, and 80% of the base work is already done. Furthermore, working this way ensures that the code is easily understood and diagnosable by any member of your automation team. In fact, that is exactly our goal today. We are going to design the ultimate standard for digital motor control. The DFB we create later will be the key piece for the next video, where we will learn how to use Excel macros to automate the entire instantiation process, multiplying our efficiency and drastically reducing programming times. Another functionality closely linked to the use of DFBs is the use of Derived Data Types, or DDTs. While the DFB serves to encapsulate and group logic, code, and actions, the DDT serves to encapsulate and group data, variables. Let's look at a very simple example to see it clearly. Imagine we want to send commands to our motor from a SCADA. We will need several signals, a variable for start, another for stop, another for reset, and perhaps another to select auto mode. Without a DDT, you would have to create those 4 separate variables and connect them one by one to 4 different pins on your DFB. If you have many motors, the number of variables will increase significantly, cluttering the programming. By using DDTs, instead of having all those loose variables, we create a custom structure called, for example, var_mot. Inside that structure, we put the start, stop, reset, and mode. Now, instead of passing 4 separate variables to the DFB, we pass a single package that contains everything inside. This makes our code cleaner and more understandable, and will make our programming much easier. If you come from Siemens, this might result familiar, because a DDT is the same as an FB, a function block. Now that we have understood the theoretical concepts, let's look at a practical case. In this simplified example, we are going to create a block to manage and control a motor, aiming to standardize this logic so that it can be used for all motors throughout the factory. The logic to be employed is defined as follows. Motor control will be digital. That is, only start and stop will be controlled, not speed. The physical PLC input signals will be the digital running confirmation signal feedback and the circuit breaker or motor protection switch activation signal. The physical PLC output signal will be the motor run command. Additionally, the motor must be controllable from a SCADA system, adding the following control layers. It must have a signal to toggle between automatic and manual operation. When in automatic mode, manual commands will be ignored, and the PLC will control the start-stop logic. If the circuit breaker or motor protection signal is triggered, an alarm will appear on the SCADA. An alarm will also be triggered if, after issuing a run command, the motor fails to start. The block must be able to implement interlocks. Manual actions will not be permitted while this signal is active. Finally, the created block must have the capacity to track the motor's total running hours. This is to display the information on the SCADA and send the data to an MES for preventive maintenance management. To better understand the problem, let's jump ahead and see the solution in action. This way, we can better understand the process that led us here. In this case, iFix was used for the SCADA, but any other software could have been used, such as WinCC or Aviva system platform. Also note that the PLC has been simulated for testing purposes. In future videos, we will see the process for simulating it and setting up our own PLC and SCADA test environment so that you can do it yourself. That said, let's start the testing. To begin, we can see the block already created and instantiated in the PLC, with its corresponding variables assigned. To make things easier, we have created 2 types of variables. The PSMOT type variable is used for internal PLC management and has no assigned memory addressing. The varmod test type variable is used to connect the PLC to the SCADA and does have addressing. On the other hand, we have its SCADA representation. Currently, the motor is stopped, so the outer circle is gray. It is also in automatic mode, so the inner circle is also gray. When we force the automatic run command from the PLC, the motor's color changes to green. Now, if we click on the motor in the SCADA, a pop-up will appear for control. From here, we will set the motor to manual to force actions. When switched to manual, the inner circle turns orange. If we click the run command now, the motor will start. If we click stop, the motor will stop. Now, let's switch the motor back to automatic to test the interlock. From the PLC, we will force an active interlock. If we return to the SCADA, we can see that a padlock symbol has appeared over the motor, and it will not be possible to switch it back to manual until the condition is cleared. Now let's test the alarms. To do this, we'll remove the interlock to return the motor to its initial state. We are going to stop forcing the running confirmation signal so that an alarm is triggered 10 seconds after the run command is issued. After those 10 seconds, you can see that the alarm has been triggered, the motor's color changes to red, and a reset command from the pop-up will be required to start it again. After forcing the confirmation signal again, if we now turn off the circuit breaker signal, its alarm triggers, changing the motor's color to red. Let's return the motor to its initial state to verify the last functionality. Finally, we have the counter that tracks the total motor runtime. For this example, I have decided to display seconds instead of hours so we can see the increments more easily. As you can see, the counter has already accumulated the time the motor has been running since the beginning of these tests. If we trigger the run command again, the counter continues to increment. If we stop the motor, the counter stops. By clicking the Reset Timer button, the counter resets to 0. If we start the motor once more, we can see that the count has restarted. Now that we have seen the expected operation and better understand the problem, let's see how to perform this programming in the PLC. To do this, we are first going to create the derived function block and program its logic. Next, we will create the required derived data type variables. And finally, we will instantiate and initialize the block within our program to be able to verify it from the SCADA. To access the DFB editor, we can do it from two places. From the project browser, by clicking on the Derived FB Types section, or from the general variable editor, and then going to the DFB Types section in the top dropdown. To create a new block, we will create a new entry in the table. To do so, we will click on the next empty row and enter the name of our new block. For our case, we are going to call it motor_dig to quickly identify that it is a digital motor, which only has start and stop control. Once we have created it, if we expand it, we can see all the block components we explained earlier. We are going to start by declaring the variables, beginning with the inputs. In this section, we are going to identify 3 fundamental signals that the block needs to receive from the outside to function. The first is runConf, which will give us the physical confirmation from the contactor, followed by TP, which represents the status of the circuit breaker. Finally, we will add LCK for the interlocks, But notice that in this case I have selected the word type instead of a simple Boolean. We do this for scalability, since through a single word we will be able to manage up to 16 different interlock conditions, making the block pin much more compact and professional. Once we have identified them, to add them, we simply write the name of the variable in the first cell, and in the type cell, we select the variable type. Since they are digital inputs, the type will be bool for all of them, except for the interlocks word. I'm going to copy and paste the declarations we made in the example block to speed up the process. It is also advisable to add a comment to the declarations to make the DFB more understandable. Following with the outputs, we will identify the variables that represent the results the block sends to the outside. Here we will need the Pout variable, which will be the physical output to the drive that will start the motor, and the word type variables, alarms, and state, where we will pack all the faults and operating statuses for the SCADA in an organized way. We have decided to use the word type instead of multiple Boolean variables for reasons of cleanliness and efficiency. This way, we avoid cluttering the right side of our block with dozens of pins, maintaining a much more compact and professional design. Furthermore, this greatly facilitates communication with the monitoring system by sending all the information grouped into a single package. Notice that when working with words, it is essential to add a detailed comment in the variable description. In this comment, we will indicate exactly what each bit within the word represents. For example, specifying that bit 0 corresponds to the thermal fault, or bit 1 to the confirmation fault. This roadmap is what will allow us, or any colleague in the future, to quickly identify what is happening in the motor without having to dive into the internal logic. Finally, we will include runCNT of type real, which will be the value of our timer counter. To add them to the editor, we will follow the same process as with the inputs, defining their names, types, and as we just saw, those descriptive comments that are key for good standardization. For the input and output variables, or inputs-outputs, we will declare our command word CMD. By identifying this variable in this section, we are creating a bidirectional channel between the block and the outside, allowing information to flow in both directions through the same pin. This is what allows the block to perform handshake logic or acknowledgement. Imagine it as a constant conversation between the SCADA and the PLC. The SCADA writes a value in the variable to request an action, like starting the motor, and the DFB, after reading that request and executing the internal logic, automatically writes a 0 in that same memory address to confirm that the order has been processed. This technique is fundamental for two compelling reasons. First, for safety, since it prevents an order from getting stuck or active indefinitely if, for example, we lost communication with the SCADA right at the moment of the maneuver. And second, for programming cleanliness, since it guarantees that our interface buttons always work as physical push buttons. The operator presses, the PLC executes, and the system resets itself, remaining ready for the next order without the need to program edge logic or additional resets outside the block. Visually, you will see that in our DFB instance, these pins are easy to recognize, as they appear with a line connecting the left side to the right, indicating that we are working with a direct reference to the same variable. In terms of public variables, in this design we are going to opt not to create any. The reason is that all the information we want to expose to the outside has already been included more efficiently in the state and alarm words of the outputs section, so leaving this table empty helps us keep the block more hermetic and robust. Finally, we will finish with the private variables, which represent the true internal gears of the block, that operational part that works in the shadows and that we don't need to expose to the rest of the program. In this section, we will identify and declare essential auxiliary variables to make our logic readable and functional. On one hand, we will define the individual bits that we will later unpack from our command word, such as CMD_arun, CMD_mrun, or CMD_stop. This will allow us to program the logic using clear and descriptive names instead of abstract bit numbers, reducing errors. On the other hand, we will declare the status memories, such as strun, stautoman, and the autosp variable. These variables act as the short-term memory of the block. being responsible for remembering if the motor was on in the previous cycle or managing the transfer between modes without the motor stopping. We will also create the alarm memories, which in this case will be ALTP for the circuit breaker and ALCNF for the run confirmation alarm. Furthermore, a critical point of this section is the declaration of our timers ton_failCNF and ton_running as ton data types. By defining them here as private variables, we are applying the concept of multi-instance in its maximum expression. This means that every time we create a new motor in our project, the PLC will automatically assign its own internal timers, fully encapsulated and protected. In this way, we completely forget about having to manage global timers or external time bases, guaranteeing that a motor's time count is completely independent and never interferes with another's. Once all variables are defined, it is time to program the code. To do it in an organized way, we are going to adopt a professional structure by dividing our DFB into 4 distinct sections. This organization aims to take advantage of the environment's flexibility to mix programming languages as they best suit each task, clearly separating responsibilities within the code. In this way, we will first design a section called Version, intended exclusively for comments on versioning and modifications. Then a section called Inputs, in charge of preparing and translating the signals that come from the outside. Next, the Output section, which will do the reverse job by packaging the results. And finally, the Logic section, which will be the real brain of the system. By structuring it like this, we gain a huge advantage in maintenance. If tomorrow we have a communication failure with the SCADA, we will know that we must review the input or output sections. Whereas if the problem is operational with the motor, we will go directly to the logic, saving a lot of diagnostic time. To create the sections, we simply write over an empty row in the sections area. When we have entered the name we want to assign to the first section, pressing Enter will open the configuration pop-up. From this pop-up, we can finish adjusting the name of the section and, most importantly, select the programming language. For this section, we will select Structured Text, symbolized by the initials ST. We also have more options in the other windows, but for now we are not going to modify them. If we now double-click on the section we just created, the code editor will open so we can start programming it. Once inside the editor, and even though we have chosen structured text, paradoxically we are not going to write any instructions that the PLC must execute. The function of this section will be to act as the identity sheet of the block. Here we will write, exclusively through comments, the current version of the DFB, the date of the last modification, the author, and a brief description of the changes made. Although it may seem like a trivial step, in the industrial environment this section is critical, as it allows any technician who comes across this block in 2 years to instantly know if they are working with the original version or a patched revision, turning the block into its own documentation and saving hours of future diagnostics. Once we have filled this section with comments, we are going to create the next section, the Input section. When creating this section, we will do it using block language, or function block diagram. This language has been chosen because, as it is a task of signal mapping and distribution, visualizing the connections as if they were cables will be much more intuitive. The main objective of this section will be to perform an unpacking task. We will take our CMD command word, which arrives from the SCADA with all the information compressed into a single register, and connect it to a block called word to bit. To add this block, we can do it from 2 places. In the top project menu, from the data selection icon, on the function and function block types section, we can filter by the name of the block we are looking for. We must also make sure to have the corresponding type selected on the right side. By selecting the type and clicking on our section, the block will be added. The other way to add it would be from the FFB Input Assistant icon. When clicking, a pop-up will open to select the block. From here, the same window as before will open, and the rest of the procedure will be the same as in the previous case. With the block already placed on the canvas, we will proceed to connect our CMD variable to its input, the left side. By doing so, we will have immediate access to the breakdown of its 16 individual bits on the right side. It is at this point that we will carry out the final assignment, wiring each output of the block in an orderly fashion to its corresponding private variable. We will assign bit 0 to our automatic run variable, bit 1 to manual run, bit 2 to stop, and so on with the rest of the commands. In this way, we manage to transform a numeric and abstract word into a series of clean signals, properly identified, leaving the ground perfectly prepared for the logic to work with clear and understandable data. Once we have it ready, we are going to create the output section, where we will do the opposite of the input section. We will continue using FBD language, as the visual logic helps us perfectly understand how we build the information that leaves the block. If before we unpacked, now our objective is to pack, we are going to collect all those status and fault signals scattered throughout our code and group them into ordered registers to send them to the SCADA in the most efficient way possible. To do this, we will insert the inverse block to the one we used previously. In this case, we will need 2 instances of this block. In the first one, we will build our alarms word, connecting our private fault variables on the left side, the block's inputs. We will assign, for example, our thermal alarm to bit 0 and the confirmation fault to bit 1. The resulting output, which is already a complete word, we will connect directly to our alarm's output variable. We will repeat the process with the second block to form the state word. Here, we will map the key operating indicators, connecting the physical output signal to the first bit to indicate if the motor is running, and the mode signal to the second bit to indicate if it is in manual or automatic. Upon finishing, we will connect the result to our state variable. In this way, we ensure that by reading just 2 registers, the supervision system has a complete, compact, and updated snapshot of the motor's health and status in each cycle. Once we have the inputs and outputs part ready, we can start programming the block logic. To do this, we will create a section called Logic, and we will do it with structured text language. To keep the code clean and orderly, I have divided it into 6 functional blocks using comments. Let's look at them one by one. In the first block, we evaluate the alarm condition of the circuit breaker. By default, when the circuit breaker is armed, we receive a true signal at the physical input, and when the circuit breaker is tripped, we receive a false. Therefore, the alarm occurs when we do not receive this signal, so it will simply be enough to assign that negated signal to the alarm variable. In the second block, we evaluate the run confirmation alarm. Here we will use our instance of the ton fail (CNF) timer to detect a discrepancy. The logic is simple. If we are ordering the run, P out, but we do not receive the physical confirmation, run conf, the timer starts counting. If this situation persists for more than 10 seconds, we activate the confirmation alarm ALCNF. Notice that we use an IF block to latch the signal. Once the alarm is activated, it remains true until someone explicitly resets it, preventing it from disappearing on its own if the motor stops. In the third block, we perform command processing, where we implement the handshake logic, that is, a confirmation mechanism, where the block receives the command, processes it, and automatically clears it to avoid repetitions and confirm its execution. It is activated when a new command is detected, meaning that the word of the command variable is greater than 0, which means that it only executes if the SCADA has sent some command. First, we manage the mode change. If we receive the auto or manual command, we update our internal variable st_automan. After that, we evaluate the run command, and this is where we apply operational safety. We use an if-else structure to distinguish the mode. If we are in manual, we only accept the cmd_mrun command and, very importantly, we verify that there are no active interlocks or alarms. If we are in auto, we only accept cmd_arun, completely ignoring the manual buttons. We also manage the stop command here, which for safety has priority and turns off both memories, and the alarm and counter reset commands. And to finish, we end up resetting the command variable to 0. With this instruction, we clear the command we just received, completing the handshake cycle and leaving the channel clean for the next request. In the fourth block, we program a bidirectional synchronization. If the motor is in manual, we make the auto set point track the manual one, and if it is in auto, we do the opposite. What do we achieve with this? That if the motor is running and the operator changes the mode selector in the SCADA, the motor does not stop suddenly. The new mode instantly inherits the state of the previous one, allowing a smooth and continuous transition. The fifth block acts as a containment wall. Before activating the physical output, we check if there is any critical condition. If there is a thermal alarm or confirmation fault, we immediately force all memories and the output to false. This logic has absolute priority over everything else. If there are no faults, then yes, we allow the physical output P out to copy the state of our run memory ST_run. Finally, we end with the statistics block. Here we use the second timer, ton running, configured as a 1-second pulse generator. The condition is that the motor is running and confirmed. Every time the timer completes 1 second, it resets itself, and we add that time to our counter run, CNT. In this way, we accumulate the operating time precisely, a fundamental piece of data so that the maintenance department can plan its preventive reviews. I have left the conversion to hours commented out so that from the SCADA, we can see this counter increase during the tests. If we return to the Data Editor window, we can observe that the block we are developing has a warning to the left, indicating that our block is not yet ready for use. To commission it, we must compile it first. To do so, we must right-click on the row of our block and select the Analyze Type option. Since in this case there are no errors, after compilation, the block will be ready for use. In the event that there were any compilation error, the compilation errors would appear in the bottom tab, and the block would continue with the warning and without being commissioned. Since we have it ready now, let's try instantiating it. To do this, we are going to insert it into our program in the Motors section. Once we have opened the section to insert it, the procedure to follow is the same as we did in the Inputs and Outputs sections. From the data selection icon, here we will now filter by the name of our block type, which is motor dig. Upon instantiating it, we can observe how at the top of the block, the name of the instance has been set by default to Motor Dig 1. We want this instance to have the name of our motor reference, which will be MOT4321. To rename it, we must right-click on the block and select the Data Properties option. This will open a window on the left side, where we can modify several of the instance's properties, including the name. For our case, we will rename it with the name described before. If you made it this far, congratulations! We have already completed the most difficult part of the video. We only have left to initialize the variables and test the block in the SCADA. If we return to the variable editor and go to the function blocks section, we can see all the block instances we have in our program. This is important because if, for example, we delete any instance from our program code, such as emot1234, it will still be declared and will appear here. To delete it completely, we must also delete this declaration. Let's move on to the initialization of variables. To do this, we are going to create 2 derived data types. One in charge of connecting the process variables with the SCADA, and another in charge of managing variables internally in the PLC. This way, every time we want to add a new motor, it will be enough to declare these 2 variables, and we will save ourselves from having to create a variable for each parameter. To access the declaration menu for the derived data types, we can do it from 2 places. On the left, in the project browser, by clicking on DDT types, or from the data editor, by clicking on the DDT types section. Once here, we will start by creating the internal management variable in the PLC. To do this, we will click on an empty row and put the name we want to assign to our new variable type. In our case, it will be called PS_MOT_DIG, referring to the fact that it carries the physical field readings. The 3 physical field signals were the run confirmation, the circuit breaker, and the run command output. Therefore, we will declare them as bool. Let's move on now to the communication variable with the SCADA. We will name it as var_mot_dig. and we will assign it the parameters we defined before that communicated with the SCADA. These parameters were the command word, the status word, the alarm word, the interlocks word, and the motor running time counter. Once we have them ready, we will have to go through the same compilation process to be able to commission them and have them ready for use. To declare them, we will go to the Variables section, where all the variables of our project appear. Make sure you have the DDT box checked in the upper right part to be able to see this type of variables. We will start by declaring the internal PLC variable, which we will call motor4321 internal. The important part is here. In the Type column, we will select or write the variable type we created before, which was PS_emote_dig. If we expand it, we can see the parameters we configured before. We are now going to declare the communication variable with SCADA, which we will call motor4321_SCADA. We will select the var mot dig type, and we will assign it addressing to be able to access it from the SCADA. It will start at word 200. If we expand it, we can see that each parameter has its own address. Here it is important to make a clarification. When creating a DDT that is going to have addressing, it is recommended that all the variables it contains occupy the same bits. This way, there will be no problems with addressing. In this case, the word type and the real type occupy 16 bits, so we have no problems. If, for example, we had included a Boolean variable, the program would have assigned it a word, which in that case would not be optimal. That said, let's continue. We are going to assign the variables to our instance. To do this, we will click on each pin and write the name of the corresponding variable. To access each attribute within our variable, the syntax to follow is name of the variable, followed by a dot and the corresponding attribute. Finally, we are going to make a couple of tweaks to the program sections in charge of reading the field signals. This is done this way because one never usually works directly with the field input. Good practice is to first transfer that value to a process variable, which we will work with. Since we are in simulation, we are going to make a couple of markers behave like our physical field inputs. We will do the same with the output section to finish initializing the internal PLC variable that we created before. Now that we have it ready, we are going to rebuild the project and connect to the PLC to transfer it and be able to start the tests. Once we have the project loaded into the PLC and we are online, we are going to test the element. Initially, as we haven't forced the inputs yet, the element will be an alarm because it is not detecting the circuit breaker signal. If we go to the SCADA, where we have also added this element, we can see that indeed, both motors are in alarm state. To return them to normal conditions, we are going to force these signals to simulate their detection. If you are interested in knowing how we did the SCADA part, I recommend watching the channel's iFix series, specifically the video on dynamos. Once we have forced them, we can see how the block has stopped sending the alarm. And if we return to the SCADA, we can verify that the alarm has disappeared. Let's proceed now to set the motor to manual and force the start and stop. As you can see, it works as expected. Even the runtime counter is incrementing. By clicking on the reset button, the count resets, and when we start it again, it continues from 0. Let's try forcing any interlock to check that it blocks manual mode and the indicator appears. To do this, we will insert the communication variable with the SCADA into an animation table. From here, we will write a 4 in the LCK attribute to simulate that the third interlock has been activated. As we can see, the manual options have become invisible, and the padlock has appeared. Now let's test the automatic start of the motor. To do this, we will force the automatic start command from the PLC. To force this command, bit 0 of the word must be set to 1. That number in decimal would be 2 to the power of 0, which is 1, so we will write 1. Upon doing so, we can verify that the motor has started. Now we are going to remove the interlock and we are going to stop the motor manually. As we can see, our DFB has worked correctly. In the next video, we will see how to automate the instantiation of blocks using Excel macros. This will save us a lot of programming time. The hard part is what we have done today. We will also take the opportunity to have this macro generate the SCADA tags so that they only need to be imported, automating the process even more. And with that, we've come to the end. I hope you found it useful. Leaving a like and subscribing is the best way to support the channel, and it truly means a lot. Thanks for your time, and I'll see you in the next one.